Hi all, today we can discuss about the problems based on Fraunhofer diffraction due to single slit. The theory we have seen in the last video. In this topic, the problems are mainly based on the condition for maximum, minimum and linear width of the center maximum. See the first question. Light of wavelength 5000 angstrom falls normally on a slit of width 20 into 10 raised to minus 5 centimeter. Calculate the angular position of the first two minima on either side of the principal maximum. Light of wavelength 5000 angstrom. So lambda is equal to 5000 angstrom falls normally on a slit of width 20 into 10 raised to minus 5 centimeter. So slit width D is equal to 20 into 10 raised to minus 5 centimeter. Calculate the angular position, that is theta, of the first two minima on either side of the principal maximum, that is theta 1 and theta 2 for m equal to 1 and m equal to 2, and that also for the minimum intensity condition. So we can apply the condition for minimum in this case. The condition for minimum due to single slit diffraction is d sin theta is equal to m lambda, where d is the slit width, theta is the angle of diffraction, m is the order of diffraction and lambda is the wavelength of light used. So from this general expression, sin theta is equal to m lambda divided by d. So for theta 1, that is sin theta 1 is equal to m is 1. So 1 into lambda, that is 5000 angstrom, divided by d, that is 20 into 10 raised to minus 5 centimeter. Here it is centimeter, so angstrom we can write in centimeter, that is into 10 raised to minus 8 centimeter, that is equal to 0.25. So theta 1 is equal to sine inverse 0.25, that is equal to 14.48 degree. Next we want to find out the angle for m equal to 2. So for theta 2, m is equal to 2. Then sin theta 2 is equal to m is 2 into lambda is 5000 angstrom, that is 5000 into 10 raised to minus 8 divided by 20 into 10 raised to minus 5 in centimeter. So on calculating this, it is 0.25. So 2 into 0.25, that is 0.5. So theta 2 is equal to sine inverse 0.5, that is equal to 30 degree. So the angular position for m equal to 1 and m equal to 2 are 14.48 degree and 30 degree respectively. See the next question. A convex lens of focal length 50 centimeter placed near a rectangular slit width 0.2 millimeter produces a Fraunhofer diffraction pattern on a screen. Wavelength of light used is 5893 angstrom. Calculate the distance of first dark band from central bright. A convex lens of focal length 50 centimeter, that is f is equal to 50 centimeter, placed near a rectangular slit width 0.2 millimeter, that is slit width d is equal to 0.2 millimeter, produces diffraction pattern on a screen. Wavelength of light used, that is lambda is equal to 5893 angstrom. Calculate the distance of first dark band from central bright. In the single slit diffraction pattern, we are getting a central bright band. Then the distance of this first minimum from the central bright we can indicate as y. Then the expression for this distance of the first minimum from the central bright is y is equal to f lambda by d. The theory we have seen in the last video, where y is the distance of first minimum from central maximum, f is the distance between the slit and the screen. If the lens is close to the slit or the screen at a far distance, we can also approximate this f as the focal length of the lens. And lambda is the wavelength of light used, D is the slit width. So here in this question we want to find out the distance of the first dark band from central bright, that is Y we want to find out. So F, D, lambda values are directly given. On substituting these data in this expression we can find out the distance. So Y is equal to F is 50 centimeter, 50 into 10 raised to minus 2 meter, into lambda is 5893 Armstrong, that is 5893 into 10 raised to minus 10, divided by D is 0.2 millimeter, so 0.2 into 10 raised to minus 3 meter. So on calculating we will get it as 1.473 into 10 raised to minus 3 meter, that is 1.473 millimeter. So in the question if they are asking the distance of the first dark band from the central bright band, then we have to use the expression Y equal to F lambda by D. If in the question they are asking the total width of the central maximum, then the total linear width of the central maximum will be 2y and the angular width of the central maximum will be 2 theta. So the total angular spread of the central maximum is 2 theta and linear spread of central maximum is 2y. See the next question. A lens whose focal length is 40 centimeter forms a Fraunhofer diffraction pattern due to a slit 0.3 millimeter wide. Find the distance of first secondary maximum from the axis. Lambda of light used is 589.3 nanometer. A lens whose focal length is 40 centimeter, that is F is equal to 40 centimeter, forms a Fraunhofer diffraction pattern due to a slit 0.3 millimeter wide, that is D is equal to 0.3 millimeter. Find the distance of first secondary maximum from the axis. Lambda, that is wavelength of light used, is 589.3 nanometer. So here we want to find out the distance of first secondary maximum. At the center we are getting a central bright band, then the minimum, and the next maximum is known as the first secondary maximum. Like at this point the first secondary maximum form. Then the distance of this secondary maximum from the axis, that is from the center point, we want to find out. So let this distance be y. And for the first secondary maximum, the angle of diffraction, let it be theta. Then the condition for secondary maximum is d sin theta is equal to 2m plus 1 lambda by 2. So here we are considering the first secondary maximum. So first secondary maximum means m equal to 1. D sin theta is equal to 2 into 1 plus 1, that is 3 lambda by 2. Here we want to find out this distance of first secondary maximum from the center. So that is why we want to find out. In this expression y is not there. But this y we can find out from the concept angle is equal to arc by radius. This distance between the slit and the screen, that is considering as the focal length of the lens, that is given. So angle theta is equal to arc y divided by this f. So y is equal to theta f. So theta we can find out from this expression. That is here sin theta is equal to 3 lambda by 2d. As the angle of diffraction theta is small, we can consider this sin theta as theta. So this expression becomes theta is equal to 3 lambda divided by 2d. Then the distance of the first secondary maximum from the axis, that is y is equal to theta. Theta is 3 lambda divided by 2d into f. So on substituting these values we will get answer y is equal to 3 into lambda is 589.3 into 10 raised to minus 9 meter into F is 40 centimeter, that is 40 into 10 raised to minus 2 divided by 2D, that is 2 into distance is 0.3 into 10 raised to minus 3. On calculating we will get it 1.1786 into 10 raised to minus 3 meter, that is 1.18 millimeter. So the distance of the first secondary maximum from the axis is 1.18 millimeter. See the next question. Light of wavelength 600 nanometer is used to illuminate a narrow single slit. In the diffraction pattern obtained on the screen at a distance of 150 centimeter from the slit, the first minima appear at 5 millimeter on either side of the central maximum. Calculate the width of the slit. Light of wavelength 600 nanometer, that is lambda is equal to 600 nanometer. It is used to illuminate a narrow single slit in the diffraction pattern obtained on screen at a distance of 150 centimeter from the slit. So the distance between the slit and the screen we can consider as F, that is equal to 150 centimeter. Then the first minima appear at 5 millimeter on either side of the central bright band. So the distance of this first minimum from the center is Y, that is equal to 5 millimeter. Then calculate the width of the slit, that is slit width D we want to find out. So the expression for the first minimum distance from the central bright band is F lambda divided by D. So from this expression we can find out the slit width D as F lambda divided by Y. So substitute F as 150 centimeter, that is 150 into 10 raised to minus 2 meter. Lambda is 600 nanometer, 600 into 10 raised to minus 9 meter divided by Y is 5 millimeter, that is 5 into 10 raised to minus 3 meter. So on calculating it, 1.8 into 10 raised to minus 4 meter, that is 0.18 into 10 raised to minus 3 meter, or it is 0.18 millimeter. So the slit width in this question is 0.18 millimeter. See the next question. Parallel light is normally incident on a single slit. The central maximum fans out at a 30 degree on both sides of the direction of incident light. Calculate the slit width. For what width of the slit the central maximum would spread out at a 90 degree from the direction of incident light. Parallel light of wavelength 5000 angstrom is normally incident on a single slit. The central maximum fans out at a 30 degree on both sides of the direction of incident light. So incident light is in this direction. So central maximum fans out at 30 degree with the direction of light. That is, the central maximum is the distance between the first two minima. So on either side it is at an angle 30 degree with the incident light direction. That is, theta is equal to 30 degree for first minimum. Calculate the slit width. That is, we have to find out the slit width for angle of diffraction is equal to 30 degree for first minimum. Second part of the question is for what width of the slit, that is D, we have to find out. For the central maximum would spread out at 90 degree from the direction of incident light. That is, if theta is equal to 90 degree, what would be the slit width? To find out the slit width for first minimum, we can apply the condition for minimum. What is the condition for minimum? D sin theta is equal to m lambda. For first minimum, m is equal to 1. So this expression become D sin theta is equal to lambda. D is equal to lambda by sin theta. It is equal to 5000 angstrom, that is 5000 into 10 raised to minus 10 divided by sin 30, that is equal to 10,000 amps into 10 raised to minus 10 meter, that is 10,000 angstrom, or 1 into 10 raised to minus 6 meter, that is 1 micrometer. Now we can find out the second part. What is the slit width if the angle of diffraction is 90 degree? So this is equal to lambda by sine theta, that is lambda is 5000 Armstrong divided by sine theta is sine 90. What is the value of sine 90? 1. So the answer is 5000 Armstrong, or it is 0.5 micrometer. So if the central maximum would spread out at a 90 degree from the direction of incident light, the slit width must be 0.5 micrometer. See the next question. Calculate the angle at which the first dark band and the next bright band are formed in the Fraunhofer diffraction pattern of a slit 0.3 millimeter wide. Calculate the angle at which first dark band, that is what is the theta value for first dark band and the next bright band. So the next bright band is the first secondary maximum. So we want to find out the angle of diffraction for first secondary maximum. The slit width is given as d equal to 0.3 millimeter and wavelength of light is 5890 Armstrong. So first we can find out the angle of diffraction for the first dark band. For that we have to apply the condition for dark band, that is d sine theta is equal to m lambda. Here first dark means m is equal to 1. So that corresponds to d sine theta is equal to lambda, that is sine theta is equal to lambda by d. That is lambda is 5890 Armstrong, that is into 10 raised to minus 10, divided by d is 0.3 into 10 raised to minus 3 meter, that is equal to 1.963 into 10 raised to minus 3. So theta is equal to sine inverse 1.963 into 10 raised to minus 3. On calculating, we will get it as 0.112 degree. Next, we want to find out the angle of diffraction for the first secondary maximum. What is the condition for secondary maximum? That is d sine theta is equal to 2m plus 1 lambda by 2. First secondary maximum means for m is equal to 1. Then the expression become d sine theta is equal to 2 plus 1 3 lambda by 2. So we want to find out theta, that is sine theta is equal to 3 lambda divided by 2d, that is equal to 3e by 2 into lambda is 5890 into 10 raised to minus 10 divided by d is 0.3 into 10 raised to minus 3. On calculating it, we will get 2.945 into 10 raised to minus 3. Therefore, here in this theta is equal to sine inverse 2.945 into 10 raised to minus 3. We will get the angle as 0.169 degree. So, for this angle, we are getting the first secondary maximum. So, remember the condition for minimum and maximum in single slit diffraction pattern. For minimum, d sine theta equal to m lambda, and for secondary maximum, d sine theta is equal to 2m plus 1 lambda by 2. See this question. A slit of width 0.16 millimeter is illuminated by light of wavelength 5600 Armstrong. Find the half angular width of central maximum. What is the half angular width of central maximum? Central maximum is at the center with the maximum intensity. Then the half angular width means the angle for which the first minimum occurs, because the central maximum is the distance between the first minimum on either side of it. Then the half angular width is the angle at which the first minimum occurs. So here we can apply the condition for minimum. What is the condition for minimum? D sine theta is equal to m lambda. The slit width is given as 0.16 millimeter and it is illuminated by light of wavelength 5600 Armstrong, then half angular width theta. For that we have to consider m equal to 1 for minimum. So if m equal to 1, this expression become d sin theta is equal to lambda. So sin theta is equal to lambda by d, that is 5600 Armstrong divided by d is 0.16 into 10 raised to minus 3 meter, that is equal to 3.5 into 10 raised to minus 3 meter. So from this we can find out the theta. Theta is equal to sine inverse this value, that is equal to 0.2 degree. So therefore half angular width is equal to 0.2 degree. So to find out the half angular width, we have to find the angle for the first minimum in the diffraction pattern. See the next question. A single slit of width 1 millimeter is illuminated by light of wavelength 589 nanometer. Find angular spread of central maxima of diffraction pattern observed. Single slit of width 1 millimeter, that is d equal to 1 mm. Light of wavelength 589 nanometer, so lambda equal to 589 nanometer. Find angular spread of central maximum. What is the angular spread of central maximum? Angular spread of central maximum is 2 theta. What is the width of the central maximum? That is the distance between the first minimum on either side of the central maximum. So if we take the angular width, that is equal to 2 theta. So to find the theta value, we have to apply the first minimum condition at this point. So what is the condition for minimum? D sin theta is equal to m lambda. So first minimum means m is equal to 1. That is d sin theta is equal to lambda. So sin theta is equal to lambda by d, that is 589 nanometer. 589 into 10 raised to minus 9 divided by d is 1 millimeter, that is 1 into 10 raised to minus 3, that is 589 into 10 raised to minus 6. So theta is equal to sine inverse 589 into 10 raised to minus 6, that is equal to 0.03375 degree. So what is the angular spread of central maximum? That is 2 theta. That is equal to 2 into 0.03375 degree, that is 0.0675 degree. So this is the angular spread of the central maximum. Next question. In Fraunhofer type of diffraction at a narrow slit of width 0.2 millimeter, a screen is placed 1.2 meter away from the slit. In the fringe pattern, first minimum lie at 3.7 millimeter on either side of central maximum. Find out the wavelength of light. In Fraunhofer type of diffraction of narrow slit of width 0.2 millimeter, a screen is placed 1.2 meter away from the slit. That is the distance between the screen and the slit that we are considering as f, that is equal to 1.2 meter. In the fringe pattern, first minimum lie at 3.7 meter. So this is the center maximum. First minimum is here. So the first minimum distance from the center we are denoting by the letter y. So y is equal to 3.7 millimeter. Then find out the wavelength of light. So the first minimum distance from the central bright we can write as y equal to f lambda divided by d. Wavelength lambda is equal to yd divided by f, that is y is 3.7 into 10 raised to minus 3 meter into d is slit width, that is 0.2 into 10 raised to minus 3 meter. F is focal length or the distance between the screen and the slit, that is 1.2 meter. So I am calculating this, we will get it as 6167 into 10 raised to minus 10 meter, that is 6167 Armstrong. So wavelength of the given light is 6167 Armstrong. Next question. A light of wavelength 550 nanometer falls normally on a slit of width 2.2 micrometer. Determine the angular position of second and third minima. A light of wavelength 550 nanometer, that is lambda is equal to 550 nanometer, falls on a slit of width 2.2 micrometer. So D is equal to 2.2 micrometer. Determine the angular position for second and third minima. So we want to find out theta for m is equal to 2 and 3. Condition is minimum. Condition for minimum in single slit diffraction experiment is d sin theta is equal to m lambda. Here we want to find out the angular position for second and third minimum. So first we can find out the angular position for second minimum, that is for m is equal to 2. So d sin theta is equal to m lambda, that is sin theta is equal to m lambda by d. So that is 2 into lambda is 550 nanometer, that is 550 into 10 raised to minus 9 divided by d is 2.2 micrometer, that is into 10 raised to minus 6. So theta is equal to sine inverse of, so 0.5 is 30 degrees. So the angular position for m is equal to 2, that is for second minima is 30 degree. So second we can find out the angular position for third minimum, that is for m is equal to 3. So for m is equal to 3, sin theta is equal to 3 into lambda by d, that is 550 into 10 raised to minus 9 divided by 2.2 into 10 raised to minus 6, and theta is equal to sine inverse of, on calculating this is 0.75, that is 48.59 degree. That is angular position for third order minimum is 48.59 degree. One last question. A lens of focal length 100 cm forms Fraunhofer diffraction pattern of a single slit of width 0.04 cm on its focal plane. The incident light contains two wavelengths lambda 1 and lambda 2. It is found that fourth minimum corresponding to lambda 1 and fifth minimum corresponding to lambda 2 occur at the same point, which is 0.5 cm from the central maximum. Calculate lambda 1 and lambda 2. A lens of focal length 100 cm, that is f equal to 100 cm, forms Fraunhofer diffraction pattern of single slit of width 0.04 cm, that is d equal to 0.04 cm. The incident light contains two wavelengths lambda 1 and lambda 2. It is found that fourth minimum corresponding to lambda 1 and the fifth minimum corresponding to lambda 2 occur at the same point 0.5 cm from the central bright band. That is fourth minimum corresponding to lambda 1 and fifth minimum corresponding to lambda 2 have the same distance from the central bright band. That same distance is 0.5 cm. Then find out the value of lambda 1 and lambda 2. So to find this we can apply the condition for minimum. What is the condition for minimum? D sin theta is equal to m lambda. For fourth minimum, what will be this expression? That is for m equal to 4, this expression become d sin theta is equal to 4 lambda 1. The wavelength corresponding to m equal to 4 is lambda 1. Then the sin theta is equal to 4 lambda 1 divided by d. To find the wavelength lambda 1 from this expression, we can use the concept as theta is small, that is angle of diffraction is small. We can take sin theta as theta. So this sin theta equal to theta we can write as 4 lambda 1 by d. Now this angle of diffraction corresponding to this fourth minimum. Then we can draw the diagram like this. From the center bright band, this is the m equal to 4th minimum. Then from the central position, this angle is theta. So the distance of the fourth minimum from the central bright band is y is equal to 0.5 centimeter. So this distance between slit and screen is the focal length, that is equal to 100 centimeter. So here this angle theta is equal to arc by radius. From that we can write theta equal to y by f. So on substituting here, this theta is equal to y by f is equal to 4 lambda 1 divided by d. Then we can write this lambda 1 as y d by 4f. On substituting the values, y is equal to 0.5 centimeter into d is equal to 0.04 centimeter divided by 4 into focal length is 100 centimeter. So on calculating it, we will get lambda 1 as 5 into 10 raised to minus 5 centimeter. So the first wavelength is 5 into 10 raised to minus 5 centimeter. Now we want to find out the second wavelength, lambda 2. So for second wavelength lambda 2, we are considering the fifth minimum. For fifth minimum, m is equal to 5, then this d sin theta is equal to 5 lambda 2. Then the fourth minimum corresponding to lambda 1 and the fifth minimum corresponding to lambda 2 are the same distance from the central bright band. So we can write it as 4 lambda 1 is equal to 5 lambda 2. So what is this lambda 2? Lambda 2 is equal to 4 lambda 1 divided by 5. That is 4 into lambda 1 is 5 into 10 raised to minus 5 centimeter divided by 5. So the second wavelength is equal to 4 into 10 raised to minus 5 centimeter. So the two wavelengths in the given light are 5 into 10 raised to minus 5 centimeter and 4 into 10 raised to minus 5 centimeter respectively. So you try more questions. All the best.